Recording is rolling, so welcome to Wednesday, September 29. I know I don't have an agenda written up here, but I'll tell you exactly what we're doing. So I'm going to debrief this lab that you guys did yesterday. I'll show you guys what the ideal textbook answers would have been and a few details. Then we're going to look at a few problems from chapter 6 in your book. Your book is organized a little bit funny, but I'll talk about that when we get to it. And then I'll plant some ideas to help you guys start thinking about the lab that you guys are going to do tomorrow. So there it is. There's the agenda. Right, so friction lab. You guys remember yesterday, you were trying to figure out what is the coefficient of friction, which is a material property between two surfaces. Let's say between paper and paper. That's why I got slab weight wrapped in paper. And there's a defined way to think about coefficient of friction, which is the ratio of friction force to normal force. And that's the first half of the lab that you guys did yesterday. So you threw down a lab weight, took a spring scale, dragged it across the surface, said what's the drag force. Right. And then as long as it was horizontal and it was a constant velocity, then you can make a free body diagram that looks like this. Okay. The coefficient of friction is the ratio of these two forces, which, again, if it's equilibrium, because if you pull it constant velocity, that means these two are the same. If you pull horizontally, that means that the two vertical forces are the same. That the ratio of friction force to normal force is also represented by the ratio of pulling force to weight, which is more directly measurable. So that's one way to get coefficient of friction. Okay.
Wait, can you show it?
Yeah, go back to free body diagram. Yeah. All right. So while you guys are digesting this, remember that when you guys put the lab weight on the paper and we're pulling horizontally at constant velocity, like this. Come on here. Okay, just horizontal at constant velocity. There would have been a pulling force that would have been exactly equal to the friction force because constant velocity, right? That would be an example of equilibrium. Equilibrium just means no net force, no acceleration. Okay. And then also the normal force would have been equivalent to weight. Yeah.
How do you find a force of friction?
How do you find the force of friction? What you do is you directly read on the spring scale exactly how many newtons of force it takes to pull it. Okay? And that pulling force is equivalent to the friction force because constant velocity. Okay? So those forces must be the same. Yeah. Okay. Then I had you guys, okay, so what's the weight, what's the pulling force, what's the ratio of those two, which would be the coefficient of friction, which is actually what you're trying to find. Then I had you guys graph what is the pulling force versus the weight, which remember what those each are equivalent to. That this equivalent to friction force versus the normal force. If you wanted to think of it like that, I guess you could. And again, what I'm about to show you guys is the ideal textbook answer to that question. Oh, where'd it go? Here it is. Should have been a linear relationship like this, where the slope of that graph also represents the coefficient of friction. Why is that? Well, if the coefficient of friction is equal to the ratio of these two forces, if you cross multiply up the normal force, isn't that friction force is equal to coefficient of friction times normal force? Hey, doesn't that sound a lot like y equals mx, right? Like y equals slope times x kind of deal, right? That's exactly that relationship. So that should have been a linear relationship. Now, like always in science, if your data did not tell you that story, then, well, your data is the absolute truth, so that's what that is. But ideally, it should have been this, and then the slope of that line should be coefficient of friction. What's the equation of that line? That was the first question down here in this box. Was the equation of that line, pulling force is equal to coefficient of friction times weight. Hey, that looks like y equals mx, doesn't it? And then what does mu represent? There were probably two good answers. You could have said the slope of this line is equal to mu. You also could have said the coefficient of, kinetic friction, because it was sliding, wasn't it? Coefficient of kinetic friction. I guess if you were really careful about it, you could have gone for static friction too, but actually the second lab setup that you guys did is probably easier to find static friction. Anybody got any questions from the first half? All right, now the second half was a bit more involved, maybe took a bit more thinking. What I want you guys to do for the second half was to take different lab weights. I mean, each half you were working with different lab weights, and they're like small, medium, large, right? Maybe cover them all in paper to control for the materials. And to put it on an incline and start tipping that incline and see what angle that the lab weight broke the friction and started sliding down. Okay. Now, this is the free body diagram that went along with that, and I actually left this on the projection over the course of the lab so you could reference this and think about how this would work out. Okay. I wanted you to find a few different lab weights, then see what that angle was that it would slide down. And then I told you guys to take the tangent of that angle, but I never told you guys why. And part of this debriefing, I'm dig into that. Or some of you guys may have figured out what tan theta is about. Did anybody figure out why I want you to take the tangent of the angle? Tangent angle? Okay. All right, well, let's step through it, see if you guys can figure this out. All right, so this would have been the free body diagram at that point. Only three forces: weight down, normal force up to the left, and friction force up to the right. Of course, I'm going to break this weight to components, think of it that way, and that can help you out too. Actually, that'll lead exactly to the next step, which is to say that if this is an equilibrium, and it says equilibrium, right? That means zero net force, zero acceleration. If the block is just barely breaking friction at some point, then wouldn't the friction represent like the maximum static friction at that point? Okay. So if you found the angle to the horizontal that it would break friction, you would effectively actually be solving for static friction, wouldn't you? Like coefficient of static friction. Okay. Tell you what, if you had instead measured a slightly different angle, and that's to say the angle that the block would have been sliding down at constant velocity, which would have been a little bit shallower if you're really careful in your measurements. In that case, you actually would have also been solving for coefficient of kinetic friction, just like the first half of the lab. So, yeah, just a side thought there, but it's actually two different frictions could have been measured for. But how would this play out? How's the tangent theta enter into this? Because I see a sine and a cosine, but what the heck is tangent about? So if it's equilibrium, well, wouldn't it be true that the normal force would just be equivalent to the cosine component of the weight? Okay. You guys have seen that a lot in this class. Okay. As long as there's nothing crazy going on, that is equal to that. Okay, so that checks out. That makes sense, right? But you know what else is equal on this free body diagram? Take a look at this force, friction force. Compare that to the sine component of the weight. Okay? Now, do those two have to be equal to each other? Not universally, but they do for equilibrium, don't they? Doesn't the friction force have to balance out with the sine component of the weight? Right? Again, it could be kinetic or static, and those would be slightly different situations. But if you did the breaking point angle, then you'd be looking at a static situation. I'm going to show you guys a proof for this. So coefficient of friction is defined as the ratio of friction force to normal force. Right? But then you can make these substitutions that I wrote here in pinky. Right? I said, well, I know friction force would be equivalent to mg sine theta in the case of equilibrium. Right? This would be equivalent to this. So I can substitute that in right there. Right? And of course, normal force is the cosine component of the weight, which is, you guys have seen that a long time in this class, right? You guys know that. So sub that. Then the ratio would look like this here. And then you can say, oh, well, I got an mg on both the denominator and numerator of the fraction, so those cancel out. It's really common for mass to cancel out in this class, so the magnitude of mass doesn't matter. But hey, interestingly, the gravity field also cancels out. What that means is if you took this whole experiment to Mars, where gravity is about a third of what it is on Earth, then would this experiment play out any differently? No, everything would be exactly the same. You would actually have no idea what planet you're on just looking at the data from this graph, from this lab. So the magnitude of the gravity doesn't matter. As long as there is gravity, this whole thing works. And all you're left with is sine divided by cosine. And if that's true, what is sine divided by cosine? That is tangent. That's where the tangent theta is coming from. Actually, tangent theta is an alternate way to measure coefficient of friction. Okay. So in summary, 2 halves of the lab. The first half of the lab, you use this as your measuring tool. Spring scale measured in newtons. Right? Lifting force versus normal force. Okay, got that. But the second half lab, this is actually the only measuring tool that you would really need, because the fact that the mass and the weight cancels out, yeah, as long as you know the angle, that's all you need really to get coefficient of friction. It's kind of like a backdoor way to get it. Okay. So how would the rest of this lab paper look like? Okay, so say you were to graph tan theta versus weight. What would that be? So for various weights, right, got all these different weights. That's like my independent variable. Think of it that way. Well, were we just saying that the weight would like cancel out? Sure it does, right? Which means that this graph is going to look like what? Should have just been a constant value. Yeah, this is textbook ideal values. Maybe you got plus or minus a little bit. But all the angles that the friction broke at should have been pretty close to each other. Maybe, for example, like 11 degrees, 14 degrees, 13 degrees, 16, 10. But it should all been pretty close to the same angle, regardless of the weight. Small weights, big weights. Right? And then if the angles are all the same, then the tan theta should also have been the same. It should just been a constant line. And the value of that constant line would represent the coefficient of friction, coefficient of static friction if it was the braking angle. And that's it. Right, so two different perspectives on coefficient of friction. Right? And when I give you guys these lab papers back, I bet that the second value of coefficient of friction you got, let's say the incline one, is a little bit more than you got on the first half, the left side with the spring scales. Because the incline is more along the lines of static friction and the sliding is definitely kinetic friction. Okay? And static is always a little bit more than kinetic. Okay? You guys remember that? All right, so that's a debrief on that lab. All right, next part. All right, so every physics textbook organizes the topics a little bit differently, and throughout your textbook did this until after we were wrapping up the kinematic section, but your textbook actually, for some reason, puts projectile motion in a chapter after all the forces stuff, but also weirdly, it combines it with centripetal force, which is actually the stuff that we're starting tomorrow. So chapter 6 is like in these two different parts. It's like it has projectile stuff, and then later on it has circular motion stuff, which is not how I would have organized the book, but whatever, we're around with it. So I think a good thing to do for next few minutes is I'm just going to pick probably like 3 of these problems, I think, and solve them out for you guys. It'll be a good review of projectiles, and then maybe it'll go into some like thought process that your book was intending, right? Because this is all chapter 6, right? All right, so let's start with number 51. I think this is a pretty good warm-up problem. It says you accidentally throw your car keys horizontally at 8 meters per second off a cliff 64 meters high. How far from the base of the cliff should you look for the keys? You guys don't have this page, by the way. I didn't print it out. It's not being signed or just doing some projectile problems for review. Okay. Let me draw this out. I like this problem because I like the story of we're trying to find these lost keys. Although what's implicit here is that you would know your throwing speed. So okay, say you did, right? So we got this cliff, and according to this premise, maybe I'll change the numbers a little bit just to just want to look in the book and have a little bit different thing going. Okay. So I got these keys. So we got a key ring here, okay. And you throw off the keys at, I'm going to say V sub x because you guys know what it's going to look like. Projectile, it's going to go into a parabola shape of, I'll say 7 meters per second. That was your throwing speed. Right? You throw them straight horizontal. And let's have a cliff height of 45 meters. 45 meters. All right, so a little bit different from the book values, but just work out. Same premise. And the question is, let's say there's like a bunch of like shrubs and bushes down here, and oh shoot, we just lost those keys. Where are they? Well, if you know the height of the cliff, and you know how fast you threw them, then you should be able to calculate where they landed, x. And then we'll go to that point, we'll dig around in the bushes and see if we can find those keys. All right, so where are those keys, x? Well, I know that this horizontal speed is going to stay the same throughout the flight because there's no horizontal acceleration, as long as I ignore air drag, which is probably approximately true. Right? So 7 meters per second times however much time, well, that would be the answer, wouldn't it? The speed times however much time. Right. But I don't know the time. If only I knew how much time this was in free fall for. Where am I going to get that information from? The height of the cliff, right? So actually, let's do that. Let's start with the vertical information, figure out time from that, and then we'll go back and actually solve what's being asked for. So I'm going to start with h equals 1/2 gt squared, which is a shortened version of v naught t plus half at squared. Because remember, if you throw something horizontally and then vertically leaving your hand is not moving up or down during the first instant, that's why I left off the v naught t plus part. Okay. So I'm just focused on the vertical information. Okay. We're trying to solve for t. Okay. Trying to solve for t. Time. How much time? Okay. Since this is a review, I'll actually do something with you guys that I usually say with my AP students, which is to get a general expression in terms of variables. Okay. You could plug in h and g at this point, but what is t in general in terms of like any height, any g? Well, like cross multiply it to 2, divide down the g, so 2h on g would be t squared, then take the square root. And here's a general expression for how much the fall time is based on any cliff height and any planet for that matter. You get hot planets. Right? Let's see what it is for our case. We got a cliff height of 45 meters, and we got a gravity field of 10 meters per second squared. I bet so many guys, as soon as I wrote 45-meter tall cliff, you immediately knew what that time was going to be. How many guys already know how much the fall time is going to be? Who knows? The answer is hanging on a coaster behind you. You guys see dropping the ball off a cliff? If it's been falling for 3 seconds, it falls a distance of 45 meters, right? Right? Hasn't this been the college equation the entire time? It's been falling for 5 seconds. It's about 125 meters. That's what this is, just rearranges off the time. This has to come out to 3 seconds. Where's my calculator? Oh, here it is. Okay. This better come out to 3 seconds. Let's see if it does. What's the square root of 2 times 45 all divided by 10? Please be 3. Yeah, it's 3 seconds. 3 seconds. It takes 3 seconds to fall 45 meters. Right? Now, the actual question was, where should we be looking for these keys? So let's switch over and look at horizontal information. Everything we just did is vertical. It's related to vertical stuff. But you guys know the time is the same either way. Right? So that's all vertical. Let's switch over and look at horizontal information. Horizontal, there's only one equation that even applies, and that's x equals vt, because there's no acceleration horizontally. So, you know, the keys are going at 7 meters per second across the field, and they're doing that for 3 seconds. Boom, boom, 21 meters. Done. So we're going to climb down the cliff, and we're going to measure 21 meters from the base, and we're going to start looking for those keys 21 meters from the base. Right here. Everybody, okay? Yeah, pick a bit of a harder one. I think it was a pretty good warm-up one. Let's pick one that involves some angles. Let's go with number 56, archery. Number 56, archery. It says an arrow was shot at a 30-degree angle above the horizontal. I think I'll keep that angle. They say you know the blast speed of the bow and arrow. Right? So they give you a number. Maybe I'll make up a different number there. And it hits the target. What maximum height will the arrow attain? And also, how far? Okay, so if the target is at the same height the arrow was shot, say like at chest level, okay, how far away is the target? Okay, so 2 questions. Okay. Draw this out, make up my own numbers, and then we'll go solve from there. That. Let's get a big old field going. We're gonna shoot some arrows. There's this guy. He's got a bow, arrow. Here could be like a horizontal plane. Okay. I'll give him a let's say blast speed, kind of like as if it's a cannon, right? And now here's where I'm going to make up my own number. Let's call it 40 meters per second. Yeah. Well, let's keep the angle the same as the book angle, which is like 30 degrees. Kind of a nice angle. Okay. And then so hit a target that's over here. Okay. So there were 2 questions. The first question is, what is the maximum height that this arrow attains? So let's say call it h max. And then the follow-up question we'll worry about later is, how far away actually is the target? Call it x. So what is h max and what is x? Okay. Now, one thing I want you guys to see is that to answer each of those questions, we're actually talking about different time intervals. Right? So the arrow was shot at the point of the bow, that's right here. But the first question is going to this final location. And the second question is going to this final location. This is 2 different locations, right? So point A to point B versus point A to point B. Initial to final versus initial to final. I guess so. But you guys see that the ratio of times is going to be a 2-to-1 ratio in terms of time. Okay. So think about that. That might help out. Okay. First question first. How high does the arrow go? Let's look at the point where it's blasted off and zoom in on that. Okay. So I know it was at 40 meters per second at a 30-degree angle above the horizontal. 30 degrees. Okay. That's mostly to the right, but a good deal up. Also, let's start by quantifying what those components are. Okay? How much strictly horizontally, how much strictly vertically was that arrow shot? Okay? The vertical part, let's do the vertical part first. Okay? This is equal to what times what? 40 meters per second multiplied by sine or cosine of 30 degrees? Sine, yeah, because it's opposite. Okay. And one reason that sine is a really good, 30 degrees is a really good angle is because sine of 30 degrees is exactly equal to what? 1/2. So wouldn't this have to come out to 20 meters per second? Okay. 20 meters per second, remember what that represents? That represents initial velocity in the y direction, which immediately starts slowing down because gravity pulls down. Okay. So that's going to change. Okay. What about Vx? Wouldn't this have to be 40 meters per second times cosine of 30 degrees? Okay. Now that one I have to use a calculator for. So what is 40 cosine 30? That looks like 34.6 meters per second. Right? And that is V sub x, which stays the same all the way across the field because it's not accelerating right and left. Ignore air drag, that would be true. Gravity doesn't pull right and left. All right, so we got that. All right, now, if I want to figure out maximum height, that's a vertical type question, which means I want to play out this vertical number. It's as if you threw the arrow straight up at 20 meters per second, you would get like the same height. You just go the same height and come back down. Okay, so I'm just going to focus on that vertical component for this question. Okay. Maximum height. If you know something about its speeds, you might figure out maximum height. Which of those three kinematic formulas is going to lead to the answer most directly? What do you guys think? First, second, or third? So, which one? How about this? I'll do 2 different ways with you guys, and for the reason that when we eventually come back to that target, I want to show you how this all connects together. Okay. The most direct way to get it is just to apply this third equation, but let me do it this way. Solve this 2 different ways. Split the paper. Okay. I'll show you this leads to the same answer no matter what. Okay. So the most direct way to do this is just to say final velocity in the y direction squared equals initial velocity in the y direction squared. Well, plus 2ax, but if I modify that a bit, if it's shooting up, gravity's pulling down, wouldn't it be minus 2gh? And if we're going to 0, I should ask you guys too, but because what is its vertical component of velocity right at the very top? It's not moving up or down at all, is it, at the very top? So that would be 0. Okay. And if that's true, that would correspond to h max. Right, so 0 meters per second. For that value, 20 meters per second, because this right here, okay, minus 2 times 10 meters per second squared, that would all correspond to some h max. So could solve it that way. Okay. Let me put that to the side and do the other setup. The other setup you could do is you could use the second equation, solve for the time to get to the top, and then take that time and plug it into the top equation and solve for x that way. Okay. And the reason I also want to do that is because I want to do something else with the time later. Okay. So do a different, completely separate roadmap. That's why I split the paper. You could do final velocity equals initial velocity plus at, but maybe I'll say it this way, minus gt. But the time I'm referring to, remember, that's only the time to get to the top. So I'm going to put a subscript 1/2 on this time because that's like half the total flight time. You guys see that? T 1/2. Okay, guys get that? Okay. Now it's still going to 0 meters per second. From 20 meters per second in the y direction, because remember, this is just vertical information. That's why I'm only care about the vertical component. Minus 10 meters per second squared for some time to get to that point, but that time only represents half the flight time. That's why it's t sub 1/2. Okay. If you rearrange this, you'll get 20 divided by 10. You get t sub 1/2 is equal to 2 seconds, which isn't the answer, but it is a middle step. Then you go back to h equals v naught t plus 1/2 gt squared. This is h max equals 20 meters per second for 2 seconds. Then, well, this would be minus because gravity's pulling down at 10 meters per second squared for 2 seconds squared. Okay, h max from there. Okay, so I've got two setups, right? The left half paper, the right half paper, different points of view, but they should lead to the same thing. Okay. You know what? Since this one's set up to solve, let me just go ahead and grab this number, see what this comes out to. There's 20 times 2 minus half times 10 times 2 squared. According to this method, the maximum height should be exactly 20 meters. Maybe I should pick different numbers. I got too many 20s floating around on this paper, but 20 meters. Okay. What about this version? So 400 divided by 20. What's 400 divided by 20? You get h max. Oh, okay, you get the same thing. I mean, of course you would. Okay. Because physics is self-consistent. So 20 meters tall. Okay. That look good? Okay. So two different points of view, two different methods, get the same h max. Okay. But again, one of the reasons I did this alternate method on the right side is because look at that time, 2 seconds. Now remember what that time represents, and I put the subscript 1/2 on it because we're going from here to here. That's only half the total flight time. Okay. The other question is, well, how far away is the target? And we've already done some of the work to get that. That's why we did this. Okay. Hey guys, what is the total flight time? I mean, if from here to here it's 2 seconds, do you think by symmetry it takes another 2 seconds to fall back down? I mean, it would, right? So wouldn't the total flight time be 4 seconds? Right? So what I'm saying is, if you take t1/2 and double it, you get the full t. Okay? So if that's true, so the fact that half the flight time is 2 seconds, the full time would have to be 4 seconds. Okay? Then how far away the target is, which is the actual question, isn't that just v sub x times the full flight time? Okay? Well, let's just pop in the values. So how far away is the target? Okay. Well, I know the total flight time was 4 seconds. Okay. And what is v sub x? You can look on this page right here, and the answer is somewhere on there. What is v sub x? Who sees it? Oh, yeah, is there? How much? Yeah, you guys are looking at this 34.6, right? See, v sub x is 34.6 meters per second. That's why we did all this trigonometry in the beginning. That's how fast the arrow is going strictly horizontally across the field. Yeah, this is 34.6 meters per second. So it's going across the field at 34 meters per second. And it does that for 4 seconds. Oh, well, if I just put 2 and 2 together, what is 34.6 times 4? The number is 138. The unit is, well, meters per second times seconds gives you meters, which is definitely good news also because we're trying to figure out how far, which would definitely be measured in meters. 138 meters away. That's where the target is. Okay. Guys good? All right, let's do one more of these review problems. How about, hitting a home run? That sounds exciting. Let's see what this is all about. 57, a pitched ball is hit by a batter at a 45-degree angle and just clears the outfield fence. So maybe it's by millimeters. 98 meters away. If the fence is at the same height as the pitch, find the velocity of the ball when it left the bat. Ignore air resistance. Ooh. Yeah, this is definitely a good challenge question for. Okay. But sketch this out and see how I put this together. I'll do this faster than I normally would, just because and just review. Okay. Right, so let's get a ground going. Okay. Home plate over here. Okay. Let's put an outfield fence right here. And what else we got? Let's say the fence itself has very minimal height. Oh, yes, it's same height as the pitch. Okay, so it's kind of a silly assumption, but and it's let's find out. It was hit at 45-degree angle, and it's, so many meters away. Okay, so just like before, I'll change the book numbers. I'll call this distance 120 meters. Let's say x equals 120 meters. And the ball was hit at a 45-degree angle. So that's like this. Right? Probably it's just a solid V. Well, maybe V hit. That's all. Just subscript. This is 45 degrees. And then the ball just barely makes it over the fence, which has minimal height according to the premise. Right? So it's going to be something like that. Right? Something like that. So what's this? What's V hit? That's the question. Right. We'll chase this down and then we'll be done with projectile review. I'm gonna see this guy hit this pitch. Where should I start on this thing? Well, how about this? Some horizontal information. There's multiple ways you can solve this. I'm just gonna do one way. Okay. You know how far it went horizontally? Hey, can we actually split this velocity into horizontal and vertical components? Probably make sense of it from there. Okay. Like whatever V hit is, this would be the sine component of that, and this would be the cosine component, playing off that 45-degree angle. 45 degrees is also very special because sine and cosine have the same value of that, right? So sine of 45 degrees ends up being square root 2 over 2, and cosine of 45 degrees is also square root 2 over 2, like 0.707. So this is root 2 on 2 times V hit, as is this one, root 2 on 2 times V hit. Okay. That's your V naught Y and your V sub X. Okay. But you can actually solve this whole thing with just the V sub X number. Okay. Let's do that. Let's say distance it goes is equal to V sub X times, I see how this is going to be troublesome. Right? Scratch what I said before, you can't solve this with just this. You actually need to incorporate both, because otherwise we wouldn't know the time. Right, so we've almost got the answer, except we're a little bit info short. So root 2 on 2 times V hit, which we're solving for, times time. And we know x is 120 meters. So if only you knew the time of flight, you could very quickly get the answer. But the time of flight is going to come out of the vertical information. Okay. So let me play off that. Now, again, multiple ways to solve this, but here's one way. As if the plate and the fence have about the same height, which it said they do, then see how the height change would basically be 0, or very close to 0? Okay. Let's play off that and get the time of flight. Okay. So I'm going to say y equals v naught yt plus half at squared. Okay. And solve for time. Now, at a glance, you might say, ooh, this looks quadratic, but it's not going to be because y is 0. So we can actually factor out a t. This number, of course, was root 2 over 2v hit. And then, well, this would be minus g over 2, which is like 5 meters per second squared. And t, factor out a t, divide both sides by t, it goes away. Okay, so save you guys a little bit. Okay. Now, 2 unknowns, but that's okay. We can solve for one in terms of the other. Add 5t over, divide by 5, and I'll get the time of flight is equal to root 2 over 2 to 5 is 10 times v hit. Okay. If you do a little bit of algebra, switch around, you'll get something like that. Okay. This is really a system of equations question, because there are 2 equations and 2 unknowns. What you see right here is one of the equations, and the other equation is the horizontal stuff. And put these 2 together like a system. Okay, like a system. Okay. But we're using substitution, and I've already set the substitution. So now the last thing to do is to bring in the horizontal information, write it right here. remember, I'll even do it the same color as I did before, so it matches. X is equal to this. Right? Okay. Now here's where you say, well, I know what the time is. The time is that expression, which I got from my vertical information. Okay? Sub that in there. I get, also we know what X is. X is 120 meters. 120 meters is equal to, see, root 2 on 2 V hit times root 2 on 10 V hit. Okay? So it's like, root 2 times root 2 divided by 2 all cancels out. And V hit gets squared. I got a 10, I'll cross multiply that. This is meters per second squared. No, yeah. Okay, so then 1200, it's going to be meters squared per second squared is equal to V hit squared. Then to get the answer, the square root both sides. Ooh, yeah, that was a good challenge question right there. Looks like V hit had to have been 34.6 meters per second. That actually does look about right because they made a major league size field, and this is, yeah, that looks like a reasonable number. Okay, about 34.6 meters per second. All right, so to recap that, if you know the angle that you hit it at and how far it went, and you have a flat field, that's enough info to ultimately figure out how fast it was hit. Okay. And to solve this, though, you need to incorporate both vertical and horizontal information. So on this paper, I've got the vertical constraint, which you can get time in terms of the hit speed. And then the horizontal information says, well, it went this far, and then, well, you still have two unknowns. So this really is a system of equations between this horizontal stuff and this vertical stuff. You can solve that with a substitution. You can substitute in time in terms of V hit from the vertical stuff. And then you have one equation with one unknown, which is just V hit, and involves a square root. And then you can get how fast that was hit. All right. Any questions about that? Okay. So I want to plant some ideas for tomorrow. Tomorrow, we're going to start centrifugal force, and we're going to kick it off with a lab. And the lab's going to look, well, something kind of like this. So I'll plant these ideas now so you guys can think about them tonight. Come back tomorrow. We'll be really ready for this. Okay. So we're going to start bringing in centrifugal force. This is the force that you need to have something go around curves, right? Like the steering wheel in a car. We're going to finally start bringing that in. And your lab setup is going to involve a PVC pipe, some string, and a couple of Play-Doh canisters. And what you're going to do is wheel one Play-Doh canister that hooked to the string around in a circle. But what's going to hold it in that circle, in a state of what you might call dynamic equilibrium, is the weight of the other Play-Doh bucket. Now, way down is the Play-Doh. So now, is the swinging bucket in true static equilibrium? No, because even if it has a constant speed, it doesn't have a constant what? Direction. See how it's always changing its direction? And velocity has two parts to it, two components. Velocity is speed and also direction. So if either one of those is changing, there's acceleration involved. This is a special kind of acceleration called centripetal acceleration. The word centripetal literally means center seeking. See, like, suppose this is flying around in a circle, like, zoom, 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 zoom. What if you were to cut the string? Right? Wouldn't this want to fly off tangent to its motion like this? You guys got that question before. So there's something that's holding it in. That's what these arrows are. There's some force that's holding it in. That's the centripetal force, which is being supplied by the weight of the hanging bucket. Okay? I do recommend, you guys know the YouTube channel Vsauce? You guys might know it. Okay? There's a really good explanation of centripetal force, a video called Spinning. So I do recommend you check that out. I don't know if I'll show it in class or not, but I do recommend it. Okay. But you guys can have 4 variables that you're going to be juggling tomorrow. You could change out the mass of this bucket that's swinging. You could change out the weight of the bucket that's hanging. That's to say, changing out the force that's providing centripetal force. You can also change out the radial size of the circle. And then, somehow you're going to have to figure out the speed of this thing, like the instantaneous speed, the tangential speed of this bucket. And there's a way to calculate that. I won't tell you today, but tomorrow I will. And then I want you guys to think about it. You might be able to figure out, how do you figure out how fast it's going around? Okay. And then there's those 4 circled variables, I circled in pink ink. There's a relationship. They all fit together in a very tidy equation. And you guys will know by Friday. See how far we get tomorrow. Great. Any questions so far? Any of that?